We are moving on to the last section before exam 3, and that's quantum chemistry. So what's the big deal about quantum chemistry? Well, if you ask the little fishies, they may not know, and you may not know either, but I think it really helps explain the world around us, but in a very, very abstract way. And the world around us that they're talking about is the world of the very, 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 very small. Okay, not baseballs flying through a baseball field. No, they're like electrons. It's like light. It's the interactions and matter of the very, very small scale. So let me give you some ideas of some experiences of why we need this quantum chemistry. And first, let me tell you, we don't have all the answers. If we had all the answers, in my mind, my simple mind, there would be one book. You'd pull it off the shelf, and it doesn't matter whether we're talking about electrons, baseballs, planets, gravity, light. It doesn't matter. You pull out that one book, and it has all the answers, right? There's one set of laws. There isn't. There's no grand unified theory, which is what all the physicists are after right now. There isn't. But quantum chemistry, as long as you're not talking about baseballs, if you're talking about electrons, this is the book you pull off the shelf. It has not been proven wrong yet. So that's why we keep talking about it. And I say yet, I don't know if it will ever be proven wrong. It's a very solid theory. What it gets into and what it produces in the modern times like now is stuff like this. This is a quantum mechanical model of a molecule. And the red spots are where the electrons are really hanging out a lot, and the blue spots are where the electrons aren't hanging out much at all. So where the electrons are hanging out is what gives the molecule its shape. And that's kind of where we're at. But let's give you an idea of why we need quantum chemistry or quantum mechanics in the first place. Okay. This is magnesium metal. I think we've used it in lab. We had to shine it up with steel wool, and that's magnesium metal. This is magnesium metal. It's just ground up. But why isn't it really shiny? There's very few instances where we can really, in this macroscopic world that we live in, that we need quantum mechanics. This is one of them. It's only quantum mechanics that can explain why this stuff is dark and black and not shiny. Okay, here's another one here. We have, what are the colors of the spectrum? The name of the dude? Roy G. Biv, right? Oh, where's this one? Roy G. Bivwa? Where's white? It's all of them, right? I can't get it too good here. All right? So I need to put something in front of the flashlight to separate out all the colors. There's the Roy G. Biv, right? Quantum mechanics is needed to explain Roy G. Biv, right? So, some more here. Now, using your spectroscope, right? You pretty much just look through it and look at the white screen, okay? And hopefully you see Roy G. Biv. Now hold it horizontal like this, right? And look at the screen there. And you see Roy G. Biv? Is the R, the O, the Y, any of them missing? Or is it just a smear of colors? It's just a smear, right? And that's kind of makes sense, I guess, right? I don't know. It's just something that people observe. However, what if you observe this? Now look at the lamp. You got to get that lamp centered right in that slit. There's a slit in the spectroscope. That's what you got to get the lamp lined up with. Okay? Get that light of the lamp lined right up in there. And you are not going to see Roy G. Biv. What do you see? See lines, don't you? Right? Like I see some red lines. I see a really bright orange one, a green one, a blue one, right? Can you see it? Right? You have to get the line in the spectroscope perfectly lined up with the lamp, and you'll see it. How do you explain that? That is a real problem. When you see Roy G. Biv, all these different colors that smear, those are all just different energies. And it makes sense, all these guys have different energies. But when you look through the spectroscope and you see that, you see those, right? You see these lines. That means the molecules that are in there that are kicking off that light, they can only have certain energies. That is ridiculous. Think about it. That means you take a baseball, and I can only throw it to Gloriana at 10 miles an hour and 15 miles an hour. That's it. Nothing in between. That's ridiculous, right? In our world, but not in when you get this tiny. No, when you get this tiny, energy's quantized is the word. There's only certain energy levels that these guys can take. And this is proof. Well, how do you answer? How do you have a theory that's going to take that into account? It certainly isn't Newton if you've had general physics, because Newton, you can throw a baseball any bloody speed you want, right? I think this is filled with helium atoms. Those helium atoms, you can't throw them at any speed you want at all, right? It's only with certain energies, certain speeds. Very, very odd, okay? So how do you explain this stuff? Well, the book goes into a lot more theory than I'm going to go into. I'm just going to cut to the chase here. Almost cut to the chase. So they had, way back when in Bohr's time, the early 1900s, they didn't have spectroscopes, but they had chunks of glass, make little prisms, and they could see like a smear when they looked at the sun. But when they looked at guys like this, they saw the lines. How do you explain it? Bohr had this great idea, right? He said that you've got this nucleus. I should make it even tinier. Make a dot. Erase that guy. It's very, very small. That this atom is essentially empty space. Because they know all this so far. The atom is almost all empty space. Because they'd blow these electrons through the really thin gold foil. And these electrons would just fly right through if they made the foil thin enough. But sometimes they just shot straight back. So that told them that there's something really hard, very heavy, but it's mostly empty space. Okay, now how do you get those lines? Well, you have these electrons, right? And they can travel certain paths, right? Maybe there's one. There's another one. And they can go on this path. Orbits, right? So you could jump from, and the farther out you are, the faster you got to be going. So if you jump in from, if an electron jumps from an outer orbit into an inner orbit, okay, that's the color blue, right? Like maybe he jumps from here into this orbit and starts spinning around in that circle, and he emits the color blue. He jumps from that one to here, maybe it's a color, I don't know, violet or something, right? So that's why you only have certain colors for certain atoms. That's what Bohr said. Now, if you are, is that show still on TV? Are You Smarter Than a Third Grader? Is it a fifth grader? Oh gosh, see, I couldn't even make the show. All right, so they say, go draw an atom, right? Don't do this. Totally wrong. Instead, this is closer. This scribbling thing is closer. Right? And the darker you make the scribbling, you just say, hey, there's more chance of the electron hanging out there. You have no bloody idea where the electron is. It's just, you could just color it in, make a really scribbly dark blob, and say, okay, and you can make whatever kind of shape you want. The more shape you give it, actually, the more energy it has, because if it's this nice spherical thing, that's the lowest energy, but you can make a blob on this side and a blob on this side, right? And just keep darkening it in, and just say, okay, 99.9% of the time, the electron's in there. Okay, well, where is it the rest of the time? I don't know. But 99.9% of the time, it's there. That is quantum mechanics. It's all probability. Okay? All right. Now, we're not going to get into the math at all. But there's one atom. And the math is complicated. There's Schrödinger equation and wave mechanics. And it's... But we have computers now. Those poor dudes way back when didn't have them. But there's only one atom that we can solve exactly and get solutions for. You know, and actually get maps, electron maps, say this is where the stuff is going to hang out, and we can draw plots just like this. Instead of coloring it in, we can actually make actual 3D plots. There's only one atom that we can solve exactly in quantum mechanics. What is it? What would you guess? Which one? Why hydrogen? You're right. It only has how many electrons? It only has one electron. That's how complicated this stuff is. It only has one electron, so we can solve it exactly. So if I can't find, well, you wouldn't know. This isn't the hydrogen lamp, but the hydrogen lamp is just a little bit different color. But if we put the hydrogen lamp in there, right, you'd see the different colors, and we can predict exactly why only for hydrogen. Okay? So it's kind of odd, but okay, so we have, well, there's our answer, H. So, and they call these solutions are referred to as, well, you can call them atomic orbitals. But I don't think the book uses this word, but I much prefer the word hydrogenic, because then it always reminds me, this is only good for the hydrogen atom, nothing else, but we're going to use it for everything else. That's what's kind of odd. We are going to use it for everything. Doesn't matter what atom we're talking about. Iron. We're going to use hydrogen solutions because we can't solve iron. Okay. Anyway, so the solutions of the Schrödinger equation for the hydrogen atom, we call them atomic orbitals. And they're these big, ugly, messy equations, but we're not interested in the math. We're more interested in the concepts and understanding them to try to understand nature around us. So we're going to have these nice 3D plots. And I kind of just mentioned before, if you can draw these blobs, and the more shape you give the blob, the more energy. So which blob up here, well, I shouldn't say blob, which atomic orbital has the most energy, would you guess, out of all these that are up here? Which one has the least energy? Let's pick on Yvette. What would you guess? Yeah, how about the least? The first one? The first one, right? You've kind of seen this. It rains. What's the shape of a raindrop? Well, yeah, it is kind of like that because it's falling and the wind's blowing around it. But if the wind wasn't blowing around, it'd be spherical, right? It's the lowest energy form. So, yeah, there's our lowest energy. We call it the 1s orbital. And the more the 2s orbital, you can't really see it, but there's nothing right there. They call it a node. Right? Already impossible things are happening. Because look at this guy. Look at the 2s orbital. This is the solution for the hydrogen atom. You give that electron a little bit of energy. It's going to jump from this 1s orbital up to this one. Okay? So it's just where the electron's hanging out. So it's hanging out in this outer part. It's bigger, or it's hanging out on the inner part. But it can't be anywhere in between. So how does it get there? I don't know. But it does it. All right? It's very odd stuff here. There's all these different solutions to the hydrogen atom, and there's more and more energies, and that's kind of what we're going to get into. Okay? So when we start talking about the 2p orbital, if you're interested in what it looks like, well, that's what it looks like. There's one in the x direction, there's one in the y direction, and there's one in the z direction. And then you have these d orbitals, and look, there's 1, 2, 3, 4, 5 different types of those. Oh, and the p's, there's 1, 2, 3 types of those, right? Okay. So let's boil this down to a table. Something that we can use to really help us out with this homework. Okay, and the upcoming quiz, upcoming exam. I really think you understand this table be able to fill it in. You can answer any question the book's going to give you, any question I'm going to give you. Okay? So let's start with, well, this is the description maybe. There's this word called shell. Okay? And really, this really determines the energy. Right? It's really where you get the energy from. Right? The other guys will influence it, but not so much. You have the shell, and then you have these layers. They're going to call them subshell. The inner layers, the inner shell. It's kind of like, well, an egg is a bad example because an egg just has a shell. But sometimes, and doesn't it happen in nature? Sometimes you get a double shell, right? An egg, you get this little chickadee, and there's a shell inside a shell. Maybe I can imagine it happening. But if it did, that's your subshell, right? Another little shell inside a shell. Okay. And then we have what we're going to call orbitals. Well, hold it. This number of orbitals. So we're going to have another quantum number. Now, what I'm really first I'm going through the description, and I'm just going to describe these different, what we're going to call quantum numbers. Because this really comes down to statistics, and if we give the complete quantum number, 1, 2, 3, all 4 of them, we can actually describe where that electron is and give it all its properties. So there's really going to be 4 of them, but I'm just describing what they are first. Okay? And then this last one is the reason for splitting. Now, what do I mean there? Everything was hunky-dory for a while. The quantum mechanics was going really good, until some dude, and I don't know what possessed them, they had this lamp going. They're looking at it through their little prism, their nice little lines. And then some guy puts a magnet right by the little lamp. I don't know why. He puts a magnet there. All of a sudden now the guy doesn't see one blue line, he sees 2 blue lines, just barely split. The red line is split into 2. Everything is split. So the only way to explain it, we need another quantum number. And it's actually taking into account that if something moves, is that energy? Yes. And the more you move, the more energy you have. And you got to kind of start getting into what different types of motion do you have. And this one is the electron actually, my fist can't rotate, but this can, right? And the spin is quantized. Can't go like this, it can only go like this or something. Very odd. Things that are happening at that level that you just really can't relate to, but so there's some splitting going on. And they're trying to explain with that. So let's put in the quantum numbers here. We have N, cursive L, M sub L, and M sub S. So these are supposed to be little m's with little cursive L, little m with a little s, cursive L, and an N. Okay? So those are the symbols. I put them in the wrong one. N, L, M sub L. Jeez, Paulina, life is not that bad. The quantum number name. Okay, we're going to have principal. Principal, angular momentum, the magnetic, and spin. Okay, so these are the names. Okay. But the real homework, and what's really coming in, where this table is really important, is this box right here. Because by giving these quantum numbers only certain values, that's the essence of quantum mechanics. These guys can't take on any values they want. If they did, there would be no quantization of energy. You could have a smear of colors. No, there are only certain lines, so these guys can only take on certain values. This is where it's all at, right here. So this is what you really got to know, I think. If you're going to burn anything in your memory, you only have so much space. This is what you want in there. Okay, so what can N be? N can be 1, 2, 3, 4, 5, and it just keeps on going on and on and on and on. Now it'd be nice if they would stop there for that little n, but you have history, and some dude didn't start with n. He said, no, it's a K shell. And they wanted these. So n could also be that. I think it's going to be more common to see n is 1, 2, 3, 4, 5. Just realize that, well, the book could also use K, L, M, N, O, P. So just count them down. If n is m, if that little n corresponds to the m shell, that's also the same as n is 3. Make sense? Okay. And then the little, now L, go from 0 all the way up to the number n minus 1. So again, we have to quantize things, and this is just how it worked out after all the math. Okay, so now there's little letter designations for these guys too. But these are the possible values. L can only go from 0 to n minus 1. And, right, only positive whole numbers, right, not 0. But they're going to want little letters for this too. So let's list these out. So L could be 0, 1, 2, 3, 4, 5, 6. And it just keeps on going. So what are the little letters? Right? The lowest L, the lowest angular momentum quantum number, S, P, D, F, G, H, I. It just gets alphabetical after that. Okay. But I don't think you're going to go much farther after D, actually, with all the homework. But it's good to know, just in case. So little l can only go from 0 on up to all the whole numbers, positive. But know the letter designations too, because they're going to use those. Okay. And then what can m sub l be? Well, you pick an L, and then m sub l goes from negative L to positive L. Those are its only possible values. Okay. And then that little m sub s can either be positive a half or negative a half. It can only be spinning in one direction or the other. There's nothing in between. Okay. Only two values. So this is a big deal. Know that darn. Know all these values. Know that n is only positive whole numbers. L goes from 0 to n minus 1. M sub l goes from negative L to positive L. M sub s could only be one of those two. Okay, so let's see what kind of homework questions we're going to be asking. And it's just getting used to the terminology, really, I think. So the question is, how many subshells in the L shell? Okay, play around with the numbers. The L shell, that means what is what? That means little n is 2, right? So that's the first thing I would write. Little n is 2. And then they're asking about subshells. So Desiree, what quantum number, what are they talking about in subshells? What little symbol? The little l. So what they want to know is how many little l's are you going to have? Right? So the big shell, you have the big egg shell, n equals 2. Well, how many little egg shells do you have inside? Well, that's what you're counting up here. So if n is 2, we said that L goes from what to what? 0 to n minus 1. So that means it really goes from 0 all the way up to, wow, in this case, yeah, 2 minus 1, or 1, 0 to 2 minus 1. So that means all little l could be is what? It can only go from 0 to 1. Wow, that's it, right? 0 and 1. Right? Can L be 0? Yeah. It's the n that can't be 0, right? Does that make sense? So L goes from 0 to n minus 1. So just put in whatever n was, whatever the shell is. You got it. Do the same for B. Do the same for B. identify all the different possible values for little l. Because subshell is just another way of saying little l, the angular momentum quantum number. So find all the different little values of l. Oh, they want to know how many, so the answer is really 2, right? For this one, how many? There's two of them, since we didn't count them up. Okay, so Taylor, this time we're in the O shell, so that means my little n is going to be 5. Okay, my little l can only go from 0 up to 4. Okay, so what are all my possible little l's then, Jacqueline? Yeah, 0, 1, 2, 3, 4. Okay, they wanted to know how many, so that answer would be 5. How many? 5. Okay. How many atomic orbitals in the p subshell? Okay. Now, Paulina, which one are they after here? Atomic orbitals. Which quantum number? I don't know the answer. I'm just wondering which quantum number are they after? Atomic orbitals. I don't know. I'm just after the table to guide you. I'm not after the final answer yet. When they're asking for the number of orbitals, number of atomic orbitals, they're after. You want to see what I'm trying to get at? Yeah, this guy. M sub L, right? So they're after M sub L. So that's all you're really, that's what I'm trying to get you to guide you to using that table, because I think it's easier that way. So M sub L goes from, here, because there's your answer. M sub L goes from what to what? Negative L to positive L. So if you can identify what they're asking for, I think life is a lot easier. Because, like, look at the one we just did, subshells. Okay, oh, that's L. That goes from 0 to n minus 1. So all you got to do is figure out what n is, and you have your answer, right, for subshells. If they're asking for a number of atomic orbitals, oh, that's M sub L. Well, he goes from negative L to positive L. So all I need is an L, and I'll have my answer, right? Okay, so what's my little L going to be, Maria? It's going to be 1. All right, you see, she identified it. It's right here. Right? So M sub L is going to go from negative 1 to positive 1. So what are all the possibilities there, Victoria? What would you list them out? Their whole number jumps. So you start with negative 1, then probably Victoria. She needs to get more sleep, Victoria. My goodness. Yesenia. Negative 1, then 0, then positive 1. So the total is, everybody? 3. Right? Okay.
So whatever it asked for, like if it was F is 3, we would just put negative 3.
Yeah, negative 3 to positive 3. Yep. Okay. Here's some more here. If the quantum number, if the n quantum number is 4, what are the possible values of L? Okay, Adelpho. What is the rule for little l? L is 0 to parentheses n minus 1. So that's going to be 0 on up to 3. Right? So the possible values would be Gloriana. They'd be what then? 0, 1, 2, 3. See, life isn't so bad, right? 0, 1, 2, 3. Okay. If L is 3, what are the possible values of M sub L, Christian? How are you going to figure that out? L is 3. What's M sub L? Exactly. ML, he said negative L to positive L. So he said negative 3 to positive 3. So my M sub L would be then, Stephanie, negative 3 to positive 3. Negative 3, negative 2, negative 1, 0, 1, 2, 3. Okay. 7 of them. Okay. Christina, how many subshells? How many subshells are in the M shell? How many subshells are in the M shell? How are you going to do this? Oh, I don't know. I have the answer, but subshells that are after. I don't see. I don't know. I'm just trying. I guess I'm showing you. I have nothing memorized. So what I do is I go by this guy, subshells. So that means that we're after which guy, which atomic orbital? Subshells. We're after little l. And that's where my brain kicks into gear. That's the part I memorize. We're after little l. So then you know that you're going from what to what then, Janet? If it's little l, you're 0 on up to n minus 1. So all I got to do is figure out what that M shell is. And remember, Jessica, that M counting thing starts at K. So that M, big M, would have to be what? Would correspond to what then? Big M would be, right? KLM 3. Yeah. Just remember that little n starts at 1, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And also starts at K. So KLMN, OP, 73. So 0 on up to 2. So how many subshells would that be? Everybody, that would be 3. How many orbitals in the F subshell? Erica, how are you going to figure this one out? We need to get orbitals. Yeah, we need to get M sub L, because the number of orbitals is M sub L, right? Okay. And what were its range was negative L to positive L. Okay. So that's my logic in figuring this out, is from the question, identify what quantum number they're after. So, well, Bianca, now all we need to know to answer this is just what little l is. What's little l going to be? All right. Who am I picking on? Bianca. It's the F subshell. Little l has to be, all right, I got to list it out. I don't remember this. 0, 1, 2, 3, 4. All right, keeps on going. Starts out with what little letter? S, and then P, D, F. There it is, 3. All right. I know, isn't that crazy? There must be some historical reason for it. They're probably each the name of some dude. I don't know. I'd be interested in knowing that, because that puts you through. Why not A, B, C, D? Wouldn't that be a lot easier? Or use the metric system somehow. Okay, anyway, little f, so now we're at little l has to be 3. See, I think you might have said 3 a long time ago, but I can't do it unless I list it all out, because I have horror memorizing things. So it's going to be -3 to +3. Okay, so if we're at -3 to +3, how many orbitals is that going to be? 7. Okay. Yeah, it starts out at S, P, D, F, G, H, I, and then it goes alphabetical after that. After F, it's alphabetical. F, G, H, I, J, K. So try to knock out the rest of these. Oh, we're about done out of time. So there's probably stuff in your folders. I need my spectroscopes back.